Hello, everyone. Welcome to a papers deep dive on Project Nanda. I'm Ramesh Raskar, professor at MIT. And Nanda stands for Networked AI Agents in Decentralized Architecture. And we're very excited about this roadmap of the agentic web. Today, we're going to cover four papers. Next slide. And we have co-authors from some of the most amazing companies that are thinking about the agentic web. Some of them are technology companies, some of them are infrastructure companies, some are hyperscalers, and of course, a lot of academic collaborators. So we really want to thank everybody who's joining in today. And if you're interested in thinking about research ideas or perspectives on agentic web and how billions, maybe trillions of agents will allow us to learn, earn, navigate, communicate, and transact on our behalf, please join our weekly meetup. So we have four papers being discussed today by various co-authors. The first one is, do we need a different DNS model for agents? So we are familiar with DNS for websites that allows us to map names of websites to IP addresses. Can we piggyback on that, or do we need something else? The next paper is, if we do decide to build a slightly different directory, slightly different phone book for these agents, how would that phone book support various types of agents? Because some agents are being built with MCP from Anthropic. Some others are about A2A that communicate with A2A protocol from Google. Microsoft is working on NL Web, natural language web. And of course, the Web3 community has been a pioneer in creating many types of agents and agentic frameworks. So how can this different type of a DNS, a quilt of registries, can support all different kinds of agents? Then we will dive deeper into comparison of different approaches of registries that different companies and academics have already proposed. Again, the Nanda quilt is an index that can support all these registries together. It'll be inclusive, but it's also important for us to understand how each of these registries is going to work. How A2A's approach of using dot well-known, how MCP registries approach of having a meta registry that the onus is on the clients, MCP clients, or Microsoft has Entrada IDs, Web3 has their own approaches. So how do they all compare, and how can we create a global lightweight index that Nanda is proposing? And then finally, we will discuss the security layer of it, because once these agents are out there navigating on the internet is a pretty scary place. So how do you authenticate? How do you have trust in this? We have some amazing co-authors and researchers and partners. So I will hand it over to Dr. Pradyumna Chari, who's a scientist here at MIT, to start on the first one about whether we need a new DNS model to support the agentic web. Thank you.
Awesome. Thank you so much, Ramesh. Welcome everyone to this session on Nanda papers. As Ramesh mentioned, we'll be talking about four of our papers in a bit more detail, so as to give you a sense of what we here as part of Project Nanda, along with our collaborators from different organizations and academic institutions are working on. I'll start first today by talking to you about why we need to start thinking about new registry architectures and rethinking how serving and hosting might look like in the web of AI agents. So let me quickly set up my screen and we can get started. All right, just a second. Perfect. Screen. All right. Welcome, everyone. Thank you so much for joining in to this session of Nanda Papers. The first paper that we'll talk to you about today is our paper titled Upgrade or Switch. Do we need a new registry architecture for the Internet of AI agents? As we move into, as over the past few years, we've seen a boom in generative AI, and over the past few months, this incredible push towards agentic AI. The web is on the cusp of a profound transformation. Uh, Despite advances in automation and event-driven design over the past several decades, the current web still operates on a largely reactive model. And as we move into a new era of agentic interactions, agent to agent communication, human agent communication, and autonomous behavior by agents, there is a question to ask, which is, does this traditional web infrastructure need a rethink? And do we need to start thinking from first principles as to what aspects of the traditional web infra can be retained, whereas what aspects need to be relooked? To better understand where we are at, it's a good idea to look at where we stand with respect to how the traditional web infra works versus how the internet of AI agents is likely to start working, moving in the future. Uh, One of the most significant differentiations or distinctions between the traditional web infra and the internet of AI agents is the fact that the traditional web infra is largely reactive. Uh, in most cases, be it web pages, HTTP request responses, API calls, or database lookups, web pages are reactive. A request is sent and a response is received. Uh, some critical characteristics include, of course, this reactive behavior, a largely stateless aspect, and human-driven interaction to a large extent. Contrast this with the Internet of AI agents as this is likely to shape into. This Internet of AI agents will, of course, involve human agent interaction, but also moving forward, autonomous agent to agent interactions. And some key characteristics of this behavior will include proactive initiative by agents, where there are agent initiated actions, stateful behavior, which means persistent memory over time, autonomous and multi step coordination, as well as critical aspects such as identity affirmation, trust in capabilities, and several critical aspects such as this. This is, of course, the high level of this distinction. And this distinction between static, stateless, traditional web infra versus LLM-backed autonomous agents is true across several dimensions, including aspects such as initiation of control, life cycle, the context of execution, state management, the level of autonomy, and several other aspects. Across all of these dimensions, you'll find that the traditional web infra, to a large extent, is broadly static, stateless, and reactive. Of course, there are exceptions as we move forward, and I'll talk about this very, very shortly. But to a large extent, there is a clear distinction between where we are moving with LLM-backed autonomous agents, namely autonomous behavior, stateful behavior, and moving beyond this reactive setting. Uh, this is a critical aspect as we move to the web of AI agents. And it's not just this behavioral aspect of AI agents that is going to be critical as we rethink what the web of AI agents should look like. But a second critical aspect is the scale. Today, we have about 5.5 billion users of the internet worldwide who are navigating over a billion websites. Yet only about 17 to 20% of those websites, which is a few hundred million, are actively maintained. As we move towards the web of AI agents, the sky is truly the limit in terms of how many AI agents we may end up with, of course, over the next decade, but truly in a matter of several years moving forward. So, for example, imagine AI agents at edge devices, personalized AI agents for every individual, task-driven AI agents that replace web pages, and so on and so forth. It's not an exaggeration on overstate or an overstatement to say that we can possibly have an ecosystem where there'll be several billions or maybe hundreds of billions or potentially trillions of AI agents out there in a matter of over the next several years to a decade. Of course, all of these AI agents will behave differently. Some of them would be ephemeral. They come and go as tasks are performed. Some of them would be static AI agents. For example, an AI agent that's performing tasks such as CRM or tax management or financial management. Some of them will perform critical tasks like medical diagnosis, whereas some of them would be less critical, like a personal agent for myself who will take care of calendars. There'll be different types of AI agents, but all at a massive scale. All this requires a rethinking of how the traditional web infrastructure looks like and what aspects of the traditional web infrastructure might potentially hit a roadblock as we approach these two aspects, which is a massive increase in scale of agent-based entities, and second, this uh, change in behavior from a reactive, stateless request response type behavior to an agentic, active, stateful behavior. Uh, so this is sort of the setup for this particular paper. And to better understand where we stand, it's also a good idea to look at a quick primer on the World Wide Web architecture and hierarchy. Of course, this is, even though this is a 20-page paper, this is again still remains a simplification, but a good point to start when we talk about what the WWW hierarchy looks like. Four aspects that we'll touch upon, that this paper touches upon in terms of the World Wide Web hierarchy. First, the domain name system or DNS, which is a globally distributed hierarchical namespace which maps human readable domain names to machine readable IP addresses. The system provides globally unique identifiers for websites in a hierarchical structure that makes it easier to route. Uh, while root to resolver updates, which means updates to DNS, can propagate very, very fast, but as a result of a lot of caching that takes place in the web infrastructure, updates to DNS can take up to several hours to 24 hours to reflect in terms of web pages or web-based applications as they stand right now. Of course, given that current web is, as I mentioned, reactive and human request response based, this doesn't seem to be a big problem as of now. Second is metadata services in general on the web, one such being the Whois database, which just complements DNS by providing metadata about domain ownership and aspects such as those. Now, important to note that Whois is not part of the critical path of the web, but is truly mostly important for just ownership information, metadata for human consumption. Of course, as we move to an agentic web, we'll also need other types of metadata, but likely for agentic consumption. Third, very critical aspect is IP addressing, which provides unique identifiers for devices connected to the internet. Two type of IP addresses broadly exist today: IPv4, which uses 32-bit addressing, uh, which limits the number of IP addresses that can exist out there. Whereas there also exists IPv6 using 128-bit addressing, which vastly increases the number of addressable uh, uh, entities. Uh, of course, IPv6 deployment remains uneven even as of today, despite several decades of it being out there. And so this raises a critical question in terms of whether the number of addressable entities, especially if you're talking about billions and trillions of agents out there, is going to be a blocker for AI agents moving forward. Final aspect is certification authorities. Today, certificates are issued for web pages and web entities that authenticate identities and enable secure communication, and they validate ownership with expiration dates and maintain revocation lists, aspects such as this. However, certificate issuing and revocation still take finite amount of time, revocation especially, uh, and as we move into an agentic web type system, this is another question to consider whether certification authorities, certification revocation uh, likely requires near instant fine-grained revocation beyond what is capable in the current infrastructure. As we move from this current web to the agentic web, it's good to think about what we had in the past as we move from what was called dial-up or telephone line-based internet to broadband. Uh, uh, as a lot of you would recall, because I also do recall this in my very, very early years, Earlier, internet used to be served via dial-up lines or telephone lines before it moved to broadband. And there were sort of several reasons why this was done back then, just because of convenience initially, because every house had a telephone line and you could piggyback on top of that to serve broadband, rather to serve internet via those lines. However, moving forward, it was very quickly realized that this is not going to be scalable, and to go from this paradigm of telephone to broadband to sort of the web, we need a change in the infrastructure itself to go from dial-up to broadband. These included bandwidth limitations that dial-up had, which was about 56 kilobits per second, which is nothing in terms of what we have today. Addressing systems for telephone lines, which would have made it very, very difficult to uh, enable sort of packet routing and switching that is critical for web serving today. Scalability limitations from telephones and aspects such as these that designers of the web at that time observed and knew that this would require a change in infrastructure from the web, from the dial-up based system to a broadband based system. But it's not just about known unknowns such as these. We also prevented a bunch of unknown unknowns uh, when we moved from the dial-up based infrastructure to broadband. These, of course, includes aspects such as APIs that we didn't know at that time would exist on the web, serving videos and content, which would have been impossible with sort of the dial-up based infrastructure, and many, many other aspects such as these. So, very important takeaway from this, which is that the broadband transition illustrated a deeper truth to us, which is that infrastructure does not just enable applications as they stand today. It shapes what kind of applications are possible in the future, which we've not maybe even conceived today. So as we are at this paradigm shift from traditional web to sort of web of agents, it is important to consider what aspects of the traditional web can remain the same versus what aspects need to be potentially changed moving forward. Because this affects not just what we can support today, but also affects what we may be able to support in the future that maybe we've not even thought about as of now. Uh, as we talk about this transition from where we are at today to where we are moving towards, it's important to note that it's not a binary transition, but it's been a continual transition that we've been at over the past few years as the web has evolved. We started with static pages and stateless fetch for files that are served on the web via endpoints. And we moved to services such as REST and GraphQL services, such so that machines and not just humans could be clients, but still in a request response based manner. Finally, we moved to sort of event-driven compute via workers and especially with the advent of cloud-based service providers that allowed for serverless functions, jobs, and bots. These workers were short-lived, bursty, but they were still able to operate within this request response type architecture. But among all of these three, after all of these three, we now arrive at where we stand at the precipice or the threshold today as we move towards the web of AI agents, where there are some critical shifts happening. Shifts in scale, shifts in the aspect of implicit behavior and autonomy that agents embody, which require aspects such as discovery, revocation, fast revocation of trust, certification of capabilities, and cryptographic proof of behavior. That was not a critical aspect in this continuum before. As we move towards all of these aspects, it is very, very important to think about how we might need to change how we think about the World Wide Web. uh, as sort of these differences or as we move toward this continuum, there are several key issues with current web infra that may be a problem point as we move towards the web of agents. These includes aspects such as latency, security, traceability of agent behavior, verification of capabilities, scalability as number of agents increase, and several other things such as governance. Uh, as we do the scaling, there are several unique crossover points. And by crossover points, we mean, of course, as the number of AI agents as they stand today, at maybe several thousands to a million AI agents that exist today, maybe the current web infra is perfectly fine to host them. But potentially, as we scale both in terms of capability and in terms of number of AI agents, we may hit several roadblocks moving forward. Uh, and there may be crossover points for each aspect of these roadblocks that we may hit that may require rethinking each of these components of the traditional web of agents. These aspects could, of course, include just the number of AI agents that may exist and whether there's a need for rethinking addressing. These also include aspects such as DNS update propagation and how fast these updates might have to be managed, especially in terms of the number of AI agents. Metadata for AI agents, such as capability, certification, discovery, all of that aspects, and of course, certificate life cycles. These all may be aspects of concern as AI agents scale and improve in the future and need to be of consideration moving forward. We also have a bunch of unknown unknowns that we don't know yet completely about as AI agents scale. These include aspects such as latency, governance, privacy, and the sort of aspects as compute confidentiality, data locality, how data is managed, and orchestration. So several problems that may be a problem, may not be a problem as agentic capability manifests and AI agents scale in the future. And so at every point, we have two, but maybe three options for every domain of the internet. We can either upgrade how the traditional web is, we can change it entirely, or we do nothing. These are the three options we have today. Uh, and to touch upon these, I'll quickly go to this table. And for each dimension, such as identifiers, which are IP addresses, or revocation latency, or identity and trust, we can either stick to what we have today, sort of upgrade where we are at today to be compatible with the traditional web infra. So be slightly more constrained, but also take into account these challenges that we've highlighted over here, or do something entirely new. Uh, each of these aspects, if you look at the paper and go through each of these aspects, you'll note that uh, upgradation involves some effort, but it's generally simpler and allows for compatibility with traditional web. And in several cases will likely solve the problem. For example, in terms of addressing, we likely will not require an entirely new type of agentic addressing at the root level or beyond IP, potentially because of uh, IPv6 aspects such as that, but also addressing several agents hosted at the same IP, but as subdomains basically. But there may be several other aspects such as metadata, capability discovery, governance, or certification that may require a critical rethink. Overall, as we look at all of these aspects that we've touched upon, uh, our conclusion is that agents are here, agents are about to come, and they will likely require at least a close look at each of these domains of addressing, certification, discovery, trust, all of these aspects. And at each of these aspects will have their own unique crossover points, both in terms of agent capability and agent scale. Below the crossover point, traditional infra works just fine, where we are largely at today. But beyond their unique crossover points, we'll have to either upgrade traditional infra to some extent or maybe potentially rethink it entirely. Our take, and which we'll touch upon just shortly in the next paper, is that we likely have to look at a hybrid approach. Some aspects will remain the same. Some aspects will get an upgrade so that they remain compatible with traditional web infra, but some aspects will have to be entirely new, such as metadata or trust or auditing, which are fundamental to agentic behavior. And this is why we need to look closely at each of these aspects and figure out what those crossover points are and be ready before the crossover point is reached so that we have the infrastructure to sustain this scale of AI agents. Thank you so much. And with that, I'll stop with the presentation of this paper. Uh, and yeah, thanks so much for tuning in for this first paper of this Nanda paper talk. Uh, if you have any questions, feel free to drop in the chat, but we'll not answer questions since this is being recorded. And very, very quickly, to keep the cadence of this presentation moving forward, we will move on to the second presentation. Uh, so just for context, this first presentation was about why we need to think about whether there needs to be a new infrastructure for this web of agents as we move towards a new web of agents type architecture. Uh, but now we are going to be moving to the second paper as part of this Nanda group of papers, which is going to talk about how this change will likely have to be sustained, or how we think about uh, enabling this change. Uh, I'll just pause for 2 minutes to figure out some camera issues on mine. In the meantime, if you have any questions, feel free to drop it in the chat. So just give me one quick second. I'm just sorting this out, and then we will very quickly move on to the second paper. Uh, if the presenters for the second paper, Jared, John, and Rekha, maybe you all can switch your cameras on and just be ready. Awesome. Great. All right. We can now very quickly get started with the second paper as part of the Nanda papers presentation, and I'm going to share my screen. Oops. All right. Okay. Thanks so much, everyone, for continuing to tune in to our second presentation as part of this Nanda Papers seminar. Uh, uh, you've listened to our description of our first paper, which talks about why we need to think about uh, potentially rethinking registry architectures as we move into the agentic web. We're now going to talk about the Nanda quilt of registries, our Nanda registry architecture that is designed to sustain this internet of AI agents as we move to this era of autonomous, self-driven, and sort of AI agents and the web of AI agents, as we call it. Uh, as we all know and agree upon, the internet is poised to host billions and maybe even trillions of autonomous AI agents that can negotiate, delegate, and mitigate or migrate in milliseconds and workloads that will likely strain DNS-centered identity and discovery. So as part of this paper, we describe the Nanda quilt registry architecture, whose goal is to envision and figure out a way to make AI agents and agentic tools on the web of AI agents discoverable, identifiable, and visible on this web of AI agents. This registry serves a few critical goals. First is to propose a quilt-like registry, which means, which I'll talk to you about exactly what it means, that supports both Nanda native agents as well as third-party agents being discoverable via the registry. The second is sort of rapid global resolution for newly spawned AI agents and to enable support for different types of agents, ranging from low stakes, fast agents to high stakes, persistent agents, very fast revocation, certification, as well as an architecture that enables detailed metadata that will be very, very critical for agentic applications. As part of this paper, we define a minimal registry architecture, which is hierarchical in nature, which we'll talk to you about very shortly. We also talk to you about why the registry is designed this way to address some of the concerns that our previous paper, which is to upgrade or to switch, talks about. And we'll talk about some critical aspects of this registry architecture that enable, we think, scalability in this web of AI agents. The first fundamental aspect of the Nanda registry is that it's a quilt of registries. It's a quilt index, a lightweight index that is able to connect to a range of different agentic registries that may exist out there. So there may be aggregators of IoT agents, decentralized agents, Web3 agents, enterprise agents, MCP servers, aspects such as all of these. The goal of the Nanda registry is to make all of these entities discoverable, visible, and identifiable via an aggregate approach. Some agents and agentic entities may be directly registered via the Nanda index, but others may be registered via enterprise indices or Web3 indices, as several of our partners are working on already. And the goal of the Nanda index is to make all of these visible. Such a quilt approach has several advantages. It allows entities to have ownership over their agents. It allows a decentralization of certification and trust enforcement, and it allows a lightweight hierarchical architecture, which will be very important as we scale into the web of AI agents. Uh, we solve several problems as part of this uh, several problems as part of this registry architecture, which can be aligned within a few key goals. The first goal is to have a lightweight reference registry, which has which is a global source of truth, but does not have a lot of write churns. So we want to ensure as much as possible that this reference index, this quilt index, has as is capable of supporting as many reads as possible while minimizing writes. The second is to enable diverse agent registration models, which means different types of AI agents as that are governed by different types of entities out there should all have a place on this Nanda quilt of registries on this lightweight index. These can include agents that are registered natively via the Nanda index. These can include agentic agents as part of enterprise registries that are not directly on the Nanda index, but are visible via an enterprise registry. It can also include enterprise governed and certified agents that are directly present on the Nanda index. And same goes for Web3 agents that also exist out there and very, very critical. Company governed or company sort of certified but visible on the registry. We think it's very, very critical to support all these types of agents on this quilt of indices or registries to ensure uh, one source of identifiability, but distributed control, governance, and trust. Third key goal is to enable endpoint agility, sub-second reachability, and also enabling scalability through decentralization. The way we do this decentralization at a high level is to have a hierarchical architecture where the registry is lean and minimal, whereas metadata and detailed information is decentralized. And we'll talk to you about this shortly. Other critical goals are privacy preservation, uh, to ensure that there are different ways to access an agent, know about an agent, while maintaining privacy of both the agent hoster and person trying to reach the agent. Uh, Next aspect is flexible routing choices, and also what does sort of routing, serving, or resolving even mean in this agentic web. Uh, and the final aspect is going from self-advertising or self-capability affirmation to an audited metadata scheme. All of these are critical aspects of this Nanda web of agents, which we'll talk to you about shortly as we move forward. To give you a brief overview of the system architecture, the Nanda sort of registry, Nanda quilt of agents has 3 levels. The first level, as I talked to you about, is a lean registry. This lean registry has minimal information such as agent ID, agent name, what we call an agent facts URL, which is a URL to a metadata schema, which we'll talk to you about shortly, a private facts URL, which is another optional routing scheme whereby you can have the same agent metadata but hosted by a private third party so that the owner of the agent does not know who is requesting it. And finally, an adaptive router URL, which is optional, which is an endpoint to reach the agent. This can be a static endpoint, but this could be an endpoint that is dynamically resolved based on the geographical location of the person. All these entries on the lean registry have, of course, a time to live and are signed to ensure they are verified. As you can note, all of these aspects on the lean registry are low churn. They do not need to be regularly written and updated because facts URLs and router URLs can be static, while the more dynamic aspects, such as updating capabilities or updating routing details, can be decentralized outside the lean registry. First level is this lean registry. The second level is a detailed agent fact schema. This agent fact schema is hosted in a decentralized fashion at every agent or agentic entity, and it's a detailed metadata schema that talks about various aspects such as capabilities, uh, 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 endpoint resolution, resolving, uh, input output schemas, and many other things that may change rapidly but are therefore decentralized. Uh, this may remind you of agent card or other similar entities from aspects such as A2A, but think of this as, of course, a sort of generalization of that, and we'll talk to you more about why that's the case. The third aspect is, of course, the dynamic resolution, which is, of course, once you've identified the agent and once you've identified the metadata of the agent, how can you be resolved to that agent accurately, rapidly, fast? And we'll also talk about that shortly. So very quickly, as I mentioned to you, the lean registry has a few specific metadata fields. These include ID, names, facts URLs, including a private fact URL, and all of these are, of course, signed to ensure authenticity. This registry architecture supports several different kinds of resolution paths. The first is a direct resolution path. If I know which agent I want to talk to, let's say I already know I've already reached out to this agent and it's just that the time to live has timed out, I just go to the registry, look up against an agent name, find the sort of resolve sort of router address via the registry and just hit the agent endpoint directly. I don't need to go to the agent facts card, nothing like that. And once I have the agent endpoint, until I hit the next TTL, next time to live revocation, I do not need to touch the registry again either. The second is resolving via metadata. Let's say I want to verify the agent facts metadata of the agent. I would, of course, first go to the agent facts, either via the facts URL or the private facts URL, and then hit the agent endpoint. The third is enterprise registry resolution as part of the Nanda quilt index, which means let's say an agent is not directly hosted on the Nanda index, but as part of an enterprise registry, we would first go to an entry in the Nanda registry that represents that enterprise. For example, company X. We would hit that endpoint, which will route us to that company's registry, which will then be potentially resolved via the facts URL or directly via the router. Of course, as I mentioned, we have privacy preserving resolution via the private facts URL so that an agent or a human that's trying to reach out to an agent via the private facts or via the facts URL can be guaranteed that the agent does not know who's reaching out to them, to check their facts so that they do some kind of optimization. And finally, there's of course the adaptive routing, where you hit the adaptive router and then you can reach out to an ephemeral endpoint, so that this can allow for distributed hosting aspects such as that. As we mentioned, this registry architecture intentionally is quilt-like, which means we can have agents that are registered directly via the Nanda registry or Nanda index, but we can route to enterprise registries such as Web2 or Web3 enterprise registries. And we can also allow for agents that are governed, certified by enterprise players, commercial players, but are visible directly via the Nanda index to allow for easier discoverability. Final aspect is this lean registry index is also distributed. Distributed similar to how DNS is distributed. And of course, today this is across several universities. We have some of our partners on this call as well. And this is distributed across several universities, of course. And this is, of course, to support scalability, to ensure robustness to aspects such as corruption and so on and so forth of databases, and several of these other aspects. So this is a description of the lean registry layer of the Nanda index. Now I'll hand over to my colleague Jared, who will talk to you about the agent fact schema as part of the Nanda registry architecture. Jared, I'll stop sharing and you can share the screen on your end.
Great. Thank you so much, Pradyumna. So I'm just sharing our paper here. Second here. Okay, do you all have that visible?
It is spinning up. Yep.
Okay, great. Thank you so much. So I'm going to talk to you about the agent facts metadata layer, and I appreciate the thorough overview of the full schema and our three-layered approach with the registry that Pradyumna has provided, and also thanks to Professor Ramesh Raskar of MIT Media Lab and the rest of our brilliant team, John and Rekha, Mahesh, others on the call. So essentially, you just heard how our lean registry achieves massive scale by staying minimal. And that's with just 120 bytes pointing to the metadata URLs at our registry layer. So now I'll show you what those URLs point to and why we needed to completely reimagine the metadata architecture that hasn't fundamentally changed since DNS in 1983. The web is experiencing a profound change, which I think we all understand and what brings us here together today. And it's really unlike anything that we've seen in the 6 decades of its history, from ARPANET in 1969, DNS in 1983. So Pradyumna provided some stats earlier. We have 5.5 billion human users on the web. Agent web browsing and activity will scale this to terascale dimensions in the trillions. So that provides really the critical question of this: how do we implement and build a revamped web architecture for agentic browsing and navigation of the web and solve the trust concerns? As in a real world context, I'll just say that building in this agentic AI space with my company Universitas AI, I recognized a real world question within education, which is, how do you handle credentials and the qualifications of different agents that they will claim? And so for several years, I've been grappling with schema for doing this. And I began working on, incidentally, before the Google A2A release in April of this year, April 9th, I actually was working on something called agent-to-agent or A2A protocol based precisely on this. So I'm very fond of the branding and felt very validated in the importance of this work. And I think that with our whole team, we saw when A2A was released and we had our Nanda launch the 15th of April, that clearly this metadata layer is something that is essential. Salesforce, we should also acknowledge, has an agent specs with respect to metadata. So the question will come from the audience, essentially, well, why do we need another agent metadata artifact? But I think that we do have a broad consensus.
Do you want to go full screen with Control L or Apple L?
Okay. Control L. Let's see.
It's a web, so you might need the three dots on
I have
the.
it in I have it in a browser right now.
Yeah,
Let's see.
yeah.
Is that
It should still work. Just do Control L.
So the three dots on the right side, maybe?
Yeah, three dots on the right. Yeah. Yeah. Present.
there you go. Okay. So essentially, why another metadata artifact? And we have a broad consensus from industry and also from our team, and which includes academia and industry, about the importance of this metadata layer. The approach, framed from these experiences in higher education, looking at things, was actually to go to first principles and think about what we need in a metadata layer, and really look at this as a superset from first principles rather than derivative of the approaches of any particular players, because we want to do this right and create an open interoperable standard that's backwards compatible and future-proof with the developments from other entities. So you'll see here in table 4, Google A2A agent card and agent fax, which we present in this paper. And just to highlight a few of the key distinctions here, you can look through here, and I'll present them. We distinguish some of the shortcomings of the current A2A model, and basically where we needed to extend the capability beyond what was developed. So I'm going to present 5 key problems that we addressed with the agent fax schema. And we realized, I think the primary one, which Pradyumna has presented beautifully, is we realized we needed to decouple identity from DNS with the metadata. So in the case of DNS, there's metadata included in addition to identity, and that works for static websites, but it's not going to work for an agentic web. So the design of agent fax demonstrates this separation of concerns. So the 5 critical problems and our superset solution with agent fax include, first, the problem of trust. And this is really the breakthrough that changes everything with respect to the development of the Internet of AI agents, or the Web 4.0. While we all recognize agents need metadata artifacts, we recognize that they need to carry verified credentials for agent capability discovery that are not merely self-declared. And so this is where we get into the point of these agent facts being verified and actually signed almost like an affidavit to the best of the knowledge of the authority assigning. They believe these facts to be true. And there are many scenarios where we can imagine this. As I alluded to initially, there's higher education where you can look at credentials, expertise, also learning certificates. And agent fax enables this through W3C verified credentials that travel with the agent. These are not static artifacts, but signed verified facts. And what makes them facts is that they're signed. There's also healthcare AI. You can, again, imagine that you want to know that the agent that you're dealing with is going to be preserving your HIPAA privacy. You need to have that verified in the agent fax layer. Supply chain, you're going to, again, want to have ability to audit with whether it's financial activity or a legal analyst. Again, you're going to want to have some level that is not just self-declared to solve the trust problem, but actually is a decentralization essentially of the declaration of capabilities, so that a third party can verify separate from the querying agent or the agent providing the agentic services. So our approach, this approach with agent fax, eliminates registry lookups and central authority bottlenecks. And this is a huge point that allows our registry to remain lean, because there's no need to go back to the registry for all of these questions about capability, all of the things that will come up in agent negotiation, because they're solved in the metadata layer. Second, which is essentially the registry bloat problem. So I think we've covered this extensively. The DNS essentially approach, which we've realized we need to revamp for this agentic web, forces you to choose with the bloat of adding the metadata into identity. And we solve this through separating the concerns. The registry stays minimal with our agent address objects. And again, those are 120 bytes. They point to the very rich and dynamic agent facts metadata layer, which live independently on agent domains. And this infrastructure is something that allows us to preserve a very lean registry and then enable the high performance that will scale to this tera scale of trillions of agents and interactions. So our paper validates this approach with a performance impact of many orders of magnitude, fewer registry writes while supporting lookup at scale. Third, we have the dynamics problem. Agents are ephemeral oftentimes. Of course, there can be persistent agents or digital twins, but many agents will be ephemeral, perhaps an agent for a Red Sox game or a Giants game. They learn and their context also changes. Even persistent agents are going to have growth and capabilities, something that Ramesh has brilliantly articulated is the wisdom economy of essentially exchanges and inference and the economic incentives that exist for agents to get smarter so they can perform better. So again, this is something that we're going to see evolve dynamically. They evolve capabilities, performance metrics, and compliance status in real time. So inspired by the first principles approach, I was taking some time back from higher education and thinking about the trust capabilities we need in the web. And as part of our effort to reimagine and rearticulate what these open standards will look like, we provided this dynamic capability discovery that touches the registry very minimally. And so the agent facts can implement a separation of concerns across the time dimensions with essentially with the time to live revocation, and the static endpoints will refresh hourly with adaptive routing tokens every few seconds. So we have essentially living facts and not static artifacts. Fourth, we have the privacy problem. And this is also a huge one. As we all know, the prompts and data that is input by users, especially in enterprise, is very sensitive. And many times the prompt and input or queries is actually the intelligence that they're very keen to preserve and protect. So we've done something very revolutionary with the Nanda quilt registry and with our implementation through the metadata layer of agent facts. Every agent facts has two URLs implementing a separation of concerns for privacy. So the primary facts URL is for speed. Again, if we know exactly what agent we want to talk to and we don't have any privacy concerns. But the private facts URL is hosted on neutral infrastructure, and this enables agent capability discovery without exposing competitive interests that may be sensitive and that the querying agent may desire to keep private. So our paper demonstrates how this identity stays hidden while getting cryptographically verified metadata for capability discovery. So in here, as you can see, section E, as I mentioned, the time to live and caching strategies, this is part of the dynamic aspect that I articulated with respect to the update of the agent facts objects, these array of data that will change dynamically through time. And finally, problem number 5 is the richness problem and just the limited context provided in initial approaches. We wanted something that is future-proof, really the category of metadata, the category of facts as a superset, which everything else can be backwards compatible with, interoperable with, and plug into. So while Google has their agent cards, while Salesforce created their own metadata artifacts called agent specs, stemming from this original first principles approach that we've been articulating and discussing from even before the time some of these artifacts came out, which was all very recent. We're all working on the same questions. We represented this superset with an agent facts that can essentially accommodate inside it the Google A2A agent card, as you see here, within the artifact. So when Google created static artifacts and also self-declared abilities, agent facts are dynamic, signed, verified facts, no more static artifacts. And our facts enable verified agent capability discovery through cryptographic signatures through continuous updates, and through independent verification. So these are really critical developments, and I think extend the value for the users and for the future of an open web greatly beyond these initial forays that have come out of industry. So for this, we're really grateful for our collaborative effort and the many brilliant minds working on these problems and on these topics. So building on all of these architectural insights, we achieved a separation of concerns to reach performance at tera scale with the architecture for the Nanda registry. I think that we'll see that this separation of concerns, this decentralization, which is part of our ethos within the Project Nanda, is something that enables much greater performance as we scale. The three-layered architecture demonstrates the registry layer with lean cacheable agent address objects. This handles only identity. The agent facts layer, rich signed JSON metadata documents, handles only agent capability, discovery, and verification of those credentials. Again, what makes them facts is precisely that they're verified. And then the dynamic resolution layer, which is adaptive routing and endpoint selection and handles the connectivity. So our paper proves the separation of concerns approach enables a greater performance beyond the bloat of one kind of consolidated approach. And I think that this distribution of these concerns and problems that we need to solve allows us to have much better performance. Our agents can now discover and verify each other's capability through multi-hop resolution without ever touching the central registry again. So again, that's one of the key points, is that we want our agents to be able to discover each other with this multi-hop resolution without needing to go back to the registry. And that is what allows us to have this lean performance. The multi-hop trust scenario, the design of our separation of concerns enables this breakthrough. Let's say agent A needs to delegate a task to agent B. This requires capability discovery and also verification of those capabilities. In a traditional system, that could be 3 registry lookups to have also the verification of the capabilities from another entity, which we could say is maybe agent C. With agent facts, agent B discovers agent B's capabilities, which cryptographically reference C's audit signature, which verify the facts, and it's all resolved through the agent's own carried credentials. They carry these agent facts metadata with them. So there's one initial lookup and infinite subsequent capability discoveries, even as those change. Our paper also has specific performance metrics that we designed for and optimized for, and that's to keep the agent facts resolution at a billion scale lookup between 50 to 200 microseconds, and the sub-second global propagation for new agents, which is something that we don't have within the current DNS architecture, and also the sub-second credential revocation for VC status lists. So this proves the concept that agents carrying verified facts enable greater capability discovery at tera scale. And this is the trust breakthrough that makes building tera scale possible. Building on the insights from Project Nanda from our team, we achieve both cryptographic trust and scalable up to the tera scale and beyond through separation of concerns. Agents carry cryptographically signed facts that enable verified agent capability discovery peer-to-peer without the central bottlenecks of needing to go to the registry every single time for the lookup. Our paper validates this approach and supports again, with the quilt, the interoperability of other entities from enterprise or civil society or Web3, et cetera, plugging into this quilt-like architecture, but having the standardization of the metadata, which enables discovery. So finally, the agent facts provide the verified metadata foundation that enables intelligent agent capability, discovery, and trust networks without central bottlenecks. And our effort is really a demonstration of how we can revamp and evolve beyond the DNS's 1983 architecture to build a trust foundation for autonomous intelligence and autonomous actions and agency at tera scale. Together, we've demonstrated through these different layers the identity layer with our agent address in the registry, the metadata layer with agent facts, and the dynamic resolution, which John will speak on, the architecture, decentralized architecture of a internet that can scale to support billions and ultimately trillions of autonomous agents. Signed, verified dynamic facts make agent capability discovery possible at the Terra scale. And so I will just say that, again, you have this description right here, agent facts represented as a JSON. We have the ID, agent name, endpoints, usage format, certification, capabilities, discovery, security. And you can imagine we can extend actually these objects in a way that is future-proof. That's just a minimal representation of agent facts schema that we can plug in the Google agent card, or we can plug in a Salesforce agent specs. And this is to have something which, again, is open source, interoperable, secure, trusted, and which extends the capabilities building on the work of others in the industry to give us something which is adaptable, flexible, and can be trusted to scale to the Terra scale of an internet of autonomous agents. And this includes both the static metadata, such as identifiers and descriptions, but also these dynamic fields, capability metrics, endpoint lists, et cetera. And all of this is bound by verifiable cryptographic signatures. So hopefully the advantages of this architecture are clear and apparent. Again, we're talking with sub-second scales, and to have a much more dynamic approach and also trusted approach through the separation of concerns that we take. And before turning over to John, I'll just say here also, as you can see, section E, the agent address object returned by the registry includes the time to live field. This defines how long the record may be cached by clients, gateways, or edge resolvers before requiring revalidation. This applies to the entire agent address object, including metadata, pointers, fax URL, private fax URL, and optional adaptive router URL. This ensures the client doesn't frequently burden the registry. For stable identifiers, TTL values are typically tuned based on the volatility of the agent state, usage frequency, and trust domain policies. So again, this is a dynamic layer, and each agent fax includes its own TTL value, which again is all cryptographically signed. So with that, I will turn over to my brilliant colleague, John Zicke from Akamai. It's an honor to be working with you as somebody who worked on the original internet. And I think we have so much brilliant contributions to this this effort. We're really honored to be working together on creating the collaborative, open, interoperable standards for the future of our Internet of Agents. And with that, thank you. If there are any questions, please put in the comments. We will get to them after the paper. And again, I think the key takeaway is by having this rich dynamic agent facts decoupled from the traditional registry in the way that DNS had architected, we're able to accommodate real world needs for dynamic, trusted, and private metadata, which enables agent discovery without bottlenecking at the registry layer and allows high performance up to terascale Internet of AI agents. Thank you. So thank you, John. I'll now hand over, and you're going to learn about the dynamic routing, which is the third layer of our HOW architecture for the Nanda registry.
So thanks, Jared. And so this section is about the dynamic resolution level, and we're going to talk about how adaptive routing or adaptive resolution would work. Okay, so you saw how the agents register themselves and their metadata. So when they're registering themselves, they're doing two things. They're doing or many things, but two of the main things are here are all my capabilities, and here's the limitations. The second thing is here's the limitations on my communications. And the next layer down, which is the fax layer, helps you do discovery. So it helps the two agents now, as opposed to the old days where everything was driven by the client and you were trying to find a server. Now we're in the situation where it's agents and they have agency and they would like to participate on whether or not they are going to be used for certain situations. So they offer up some facts about what you're going to do, and the proposed possible partner in this will offer up some interest, and there's going to be some sort of resolution, some discovery, and it's going to happen. Then the question is how do you actually start the communications between these two agents? Now, in DNS, everyone thinks that you have this path name, www.salesforce.com, and you get back an IP address or maybe a couple IP addresses, and then you say, okay, well, then I have to start communicating. So obviously this is really simple, right? There's a one-to-one mapping between this name and the IP address that you get, but that's not how it works. That would not scale. The internet wouldn't work without dynamic DNS resolution. So what happens is in the path name, there's these authoritative resolvers. So in this case, it would be com and then Salesforce and then www. So the com and the Salesforce are these authoritative resolvers that say, the world trusts me that the answer I get is I'm giving the answer for com.salesforce. And that through all kinds of security features, you can trust whatever answer that guy gives back. And what it's going to give back is this last one, this www. So who's this? This last resolver is doing a lot of dynamic work, and it's giving out IP addresses for where to get at the services that the www owns, the DNS hosts, and they're giving out different IP addresses to different clients. So if you're spread all over the world, you may get different addresses, ones that are closer to the client, so that you get to the actual servers that are close to the client. So that's a geographic closeness. You might do something that's load balancing. It might say, oh, I got a bunch of servers and I want to give I want to instead of round robbing through the client, I'm going to give a specific one. Oh, this one's overloaded, so I'm not going to give out that address as often. Or you might have to do something like protection against DOS attacks. All the bots, hundreds of thousands or millions of requests come at one time into one poor little server, one little IP address. Oh, that's going to hurt them. You can spread that all out and then have those conversations terminated without hurting the origin. So this richness of the IP addresses is implemented by a whole mess of other services that actually get between the client and the actual origin, the actual web page. And all this extra stuff that's in between is what basically makes the internet scale. So those things might be terminating the TLS connections. They might be looking into the actual request and seeing if the content already exists and it's cached and it's static and giving those answers back, and you don't have to actually bother the real server. And they might be actually scanning the requests themselves to make sure that they don't hurt the server, right? There might be some malicious things. So you can one of the things that will happen later on is, people might be giving prompt attacks against the LLMs. So you might want to inject some barriers in between it. So you're not going to be able, so that the communications between two entities on the internet really have a lot of stuff between what we think of as, oh, I'm the client and here's the server, or I'm the agent who's doing the request and I'm the agent who's giving the service. all that stuff, my nose and all that stuff is in between those two entities. So how are we going to get that kind of communications to happen inside of this agentic world? And now the rules have changed. The rules have changed in the sense that in the old days, DNS was literally client versus server. So it was initiated by the client. The server was a passive entity. We're now going to have two agents who are they're active, they have agency, and they're going to be talking back and forth between each other. And there's going to be this peer-to-peer interaction before it, and we're going to have to set up one of these peer-to-peer conversations. So that's the motivation for adaptive routing. How are we going to take the agent's name and the agents that I'm trying to resolve to, and characteristics of me, the client, like where I am, and turn that into a communications path. And so there are a couple. So the first round is to come up with, here's a couple different ways, and we're going to make it easy. If, in the beginning, just give the people the URL. So this agent has this URL. It's really static. It represents a place on which you can come and have an interaction, but it really doesn't do anything about setting it up. So that's like what the internet might have worked like in 1993-ish, kind of just around the time when the web started showing up. The other thing you might want to do is, like in DNS, you might give someone a bunch of IP addresses where the client can go off and do some policy. I want to round robin between them. I want to pick them randomly. I want to go in the order that they were given to me. And that way you can do sort of a client-based statistical load balancing is the easiest thing to go there. Or we're going to need to have some sort of adaptive routing resolution where you get back the last router is going to go off and say, oh, here are the characteristics of the client, and here's the characteristics of my agent who's registered with me. I am now going to give a URL or create a communications link, such as like, here's this message queue for an IoT system, which isn't really have a IP address, but it's, go to this place and register as this entity on this message queue. That's a perfectly legitimate communications path that could happen between two different endpoints. So to reiterate, the web would not work without these dynamic features. So we need to have a dynamic hook, like dynamic DNS, so that the last resolver in the chain can go off and create a very complicated communications path between each of the things. So you might start off with a name. Go to the registry, get back an address. The address that would be like a path name for the agent. You could have the adaptive resolvers come up with go through a bunch of work to authenticate both the client and the the requester and the service, and then come up with this endpoint that is dynamic and is customized for this interaction. And when they're done, when those two entities are done talking, or these group of entities are done talking to each other, poof, it disappears and all that stuff goes away. And so I think we're going to talk about security next. Is that who's going to talk about security?
Yeah, sounds good. Thanks so much, John. I can take over. You can stop sharing your screen. Thank you so much, John, for the insights on uh, dynamic resolution, adaptive routing. I will very briefly touch upon security because we also have Rekha who will be talking to us about deployment considerations. Uh, thing to note about this tiered architecture of Nanda, most importantly, is the aspect of credentialing, trust, and privacy as part of every layer of the architecture. Of course, Jared has talked to us about the private facts aspect in detail at the registry level. Even at the agent facts level, we've a fundamental difference between facts cards that exist today versus what we are proposing is this transition from self-advertised capability and self-advertised schemas to credentialed, audited schemas. And this will, of course, require several changes, including auditing services, auditing techniques. But at the agent facts metadata level, we intentionally allow for signed and credentialed attributes at every stage of the agent facts uh, to ensure trust in the decentralized web of agents. With this, I will hand over to uh, my brilliant colleague Rekha Singhal from TCS, who will talk to us about deployment considerations and other aspects of this registry of agents. To conclude, thanks. Rekha, you're muted. You'll have to unmute.
Oh, yeah. Thanks, Pradyumna.
Thank you, Brett.
I'll just take a minute to set my screen. Okay, I'm all set.
I'll just add something on top of what Pradyumna said, that the credentials are at each of those layers. So just I misspoke earlier just to say that it's at 50 to 200 milliseconds for the resolution for lookup at that billion scale, but that the verified credentials are at each layer of the agent facts.
Okay. Yeah, thanks, Jared. So far we have looked into the architecture of registry, which is the quilt of all other agent registries. So how do we deploy it? As Pradyumna also has articulated in the beginning, there are different ways we can have deployment of these registries. It could be locally enterprise controlled and then connecting to other registries outside. So in enterprise, or it could be industry-wide control, like with a federated industry, or it could be completely decentralized, like an open source, or mix of all these things, which is a hybrid topology, right? In enterprise, you may look at all the governance policies, the agent facts themselves are stored within the enterprise, and they will govern all the policies and compliance for the registry management, right? In the federated industry registries, the storage may be distributed, agent facts may be located in different places. However, their governance rules will be governed by a centralized body, which could be industry specific organization, which can do that. For example, healthcare or logistics may have a separate kind of governance rules. In decentralized, it's more an open kind of registration. There, since we don't have a centralized body for governance, we may need kind of a smart contracts or blockchain kind of protocol, which can do a self validation to avoid the adversaries in the whole ecosystem. And hybrid, as name indicates, you may have combinations of decentralized and enterprise or federated and enterprise. So it's a mix of the other control registry which we just spoke of. So that's one angle of it, that how do we really deploy these. Second important consideration, as we are talking of large scaling of agents registry, so that performance is a big challenge. That's the reason we talked about that architecture, a layered architecture, to serve in milliseconds and to have high throughput from the system. But further, we may need to have much more component in our full architecture. Like one of them could be edge caching, as I think John also or Jared also articulated in between that. But how this caching will happen at the edge? Will it be a hierarchical hashing or node specific caching? That has to be looked into it. It could be closer to the content data network they are working today, right? So something along this line which need to be incorporated. We may also have sharded credential verification, where You can have trust scoring happening in parallel, could be domain specific, which is more like a POP kind of concept. And I think just now the John also articulated you can have a load adaptive routers depending on workload load or geographic. So we need those kind of component as a part of serving the registry itself. And finally, this audit and monitoring hooks, because that can give us a reactive feedback and taking care of any deviation happen. So we need, as any other services, any other application, we need some open telemetry and observability to get the feedback and reorient ourselves for the good performance. So this is in nutshell what we had in this paper. And finally, I like to conclude that with this rise of autonomous AI agents, we look at four key factors. Like, we see that there is a demand on digital infrastructure, scalable identity, verifiable trust, dynamic coordination, and privacy preserving discovery, which we have addressed through our architecture. We spoke in this paper. And whatever research we are end up doing to address the large scaling of autonomous AI agent, we are contributing to other aspects as well, where we are able to build up a minimal core registry, credential agent facts, which could be leveraged by many other applications as well, apart from this Nanda AI registry, preserving discovery, federated trust, and governance. And having said that, there is a lot of future work and open problems still lies ahead for us. And many of the people who are listening or tuning in here, if you would like to contribute, please join us. We do believe that we have to look at extension of our trust layer. We have to see how do we compute this trust score in a decentralized manner. So since I talked about various deployment model, your trust score computation could depend what kind of deployment model you have. Then what kind of governance framework and revocation. That's very important. If something is not working, how do we revoke back? I think Jared again, alluded to that during the architecture description. So how do we formalize these protocols? That's another thing which we have to look into it. We have to align ourselves with the open standards and interoperability like W3C and ITF. That's another future work which we need to do it. And finally, for especially for the decentralized, we need the JKP, zero knowledge proof kind of privacy guarantee, so that we are not dependent on a sender and receiver. And there are a couple of open questions which I will just articulate very quickly in the interest of time, and you can feel to read upon in the paper as well. So we do have an open question on hosting and accessibility, how this registry will be hosted, who will be hosting it, third party hosting, a centralized party hosting. So we have an open question on that, the hosting of registry, quilt of registry itself. How do we do the discovery? I think John also was talking about it, the adaptive routing. If somebody want to discover, I need some services, where is that particular agent is residing? How do I discover it in an online fashion? Do we need all this registry to be machine readable, or does it have to be, these are all open questions, because we want to prevent the updation of the data in the registry also from adversary. So we have these kind of constraint, and we still don't have an answer to this. Terminology alignment with prior art, since people will be reading so many other communication protocol, A2A from Google, and then you have MCP already from Anthropic, and you have something from Cisco. So how do we align? How do we distinguish and complement these definition? We have to really fix that internally. The resolution flow and return semantics, same as what John was also talking about it. TTL strategy, update constraint. I think these we already talked about it. And you can see the open question which we have in terms of balancing the agility and the stability, which are opposite parameter. We have to look into it. Credential governance, adaptive routing, economic incentive. So all these are open question, and there may be many more. Please feel free to add what you feel there, which we have left out here. And if you want to pick up any of these, feel free to reach out to us. Yeah, with that, I think I conclude the paper here. Pradyumna, if you have anything else to final statement, please go ahead.
No, I think that's about it. You've done a great conclusion, Rika. Thank you so much. And yeah, thanks so much for tuning into the second paper. Thanks to all the co-presenters. Uh, so we do have two more papers left to present. We're running quite over schedule, and apologies for that. And so let's quickly move on to the third paper right now, which is presented by Aditi, Singh, and Abul. Without much further ado, I'll hand over to Aditi and Abul to present their paper. Thank you so much.
Thank you, Pradyumna. My screen is shared right now, and I have the paper open. Thanks again, Pradyumna, Chari, John, and Rekha for the detailed description about how Nanda Quilt Registry is working. So for this paper on survey of AI agent registry solution. I have Abul along with me. We will go over what our approach was towards the survey of all these registry solutions. And that basically what was our motivation and pretty much towards the introduction part. So as you can see that autonomous AI agents scale across cloud, enterprise, and decentralized environment. We may face critical challenges towards how to discover, how to identify, and how to trust agents in real time. Now, traditional systems are pretty much based upon name resolution schemes like DNS, static catalogs, and they simply aren't designed for trillions of dynamic self-directed agents. That basically will have their own capabilities, may move across domains, and form ephemeral collaborations. And that's why a registry solution is required to become like an essential piece of the infrastructure for emerging Internet of AI agents. So, as you can see over here in our initial approach, we are trying to just compare like MCP, A2A, Nanda, and then towards the end, we'll try to compare them along like different dimensions. But to kind of start with our approach of how we basically, or what was the goal behind this paper, we kind of went across to think about how AI agents would require like cloud native assistant. There could be robotic controllers. There could be AI agents could be persistent, could be goal-directed entities, and they can spin up to different coordinates. They may require long-term memory for having control flow without human prompts, and the AI agent population would be growing as we're thinking about the quilt of registries. So we may need to take a step down to decide how to identify again, how to discover, and how to trust these agents in real time. As we've been talking about, like why traditional systems like DNS or static service catalogs will assume to have like endpoints, may like owner-based trust, and may need like more of like a manual configuration. So the AI agents will be able to change location dynamically, can provide like load balancing or edge mobility, or even can have like different version updates. So what we want to have is we want to need a dynamic discovery approach where agents should discover each other at a sub-second latency, even as those endpoint would shift. There would be a need for verifiable metadata, which kind of goes back and forth, deciding on what the capabilities of AI agents are, what the versioning numbers, what security credential must be cryptographically assured, so agents can trust one another without having a centralized authorization every time. And along with that, there is a need, and I think Greg also mentioned about this, was privacy preserving interaction. That is, agents ought to hide request patterns, there would be minimized telemetry exposure, and there is a need for the zero trust resolution if needed. So, in response to all these questions, what we thought is how about start comparing it with what we have right now and these are basically phase-wise growth of how agent registry or discovery is happening at that meta level. So right over here, you can see that in our paper, we have explored MCP registry, which is essentially a centralized meta registry using MCP JSON file. We will go over A2A agent cards. Again, it uses discoverable .well node hosted at the .well-known URL with agent.json catalog. And then we'll also touch base Microsoft Entra Agent ID, although a lot documentation has not been provided yet, but there is a little bit information about Entra Agent ID as well. And then we'll touch base on Nanda quilt agent facts, trying to go over how, along with this approach of MCP, A2A, and where Nanda quilt is standing on. So this is kind of a survey from this initial approach to where Nanda is currently right now. And then we'll just give those comparisons towards the end. So just for a background of information, like if you look along, again, it's kind of a repetitive, but we are currently on that modern web where it operates on reactive client driven models in which services wait for external requests before responding. So despite having significant advancement towards like cloud automation, event driven designs, or even different architectures. Now, there's still these systems are still not what we need for trillions of agents. The agents cannot simply rely on that request and response endpoints. So, because of the agent's persistent and proactive nature, AI agent would require to have infrastructures that could provide high frequency updates. Agents will push and consume like state changes at like sub-second intervals. They might need for real-time identity resolution so that when two agents encounter each other, they would need to verify their identities immediately without waiting for DNS cache. There would be need for trustable metadata exchanges so that agents may share verifiable capabilities, credentials, and intent across heterogeneous systems and organizational boundaries. So, again, as we've been saying, that our current infrastructure, our current internet stack, built on DNS for name resolution, IP addressing for routing, and certificate authorities for trust, will not be useful for the fast moving self-directed agents. So we may have like some examples such as, let's say, revocation latency is there's state propagation, identity verification. Our current mechanism typically rely on DNXS record or X.509 certificates, which are tied to human controlled domains. Now, these methods don't map cleanly to those millions of dynamic agent identities, and there may be like potential operating under a different namespace. So with these backgrounds, we got motivated towards again going over MCP, which is basically a centralized, meaning that there is a single source of truth for metadata. Again, for trillions of billions or trillions of agents, this single source of truth may not be helpful. A2A agent are decentralized, distributing discovery responsible for multiple agents to interact with each other, and then we'll be going over again Nanda agent facts. So our focus around the comparison was mainly through these 4 core domains or dimensions. The first one is security, which is basically how the registries ensures integrity of records and metadata. Are the entities tied? Or otherwise verifiable? How resistant are the registries in terms of spoofing, poisoning, or man-in-the-middle attacks? The other dimension is towards authentication, which is how do publishers prove they own a namespace or identity, or whether authentication is through GitHub OAuth, or there's DNS TXT challenge, or whether there are some tokens. And then we do have scalability, which is basically trying to know, will these meta registry solutions would be able to handle high lookup volume and large agent populations. And then the last dimension is the maintenance, where the operational simplicity is defined, or how complex is their code base? Is the registry schema driven, decoupled from dynamic state with minimal core logic? Or even how do we evolve the schema without rewriting large part of code? So what we have done over the survey is we have applied these 4 questions along our existing registry or registry-like approaches to kind of see where we are standing currently. So we start essentially with the MCP registry. MCP stands for, again, Model Context Protocol, and Anthropic recently released the MCP registry. It is a centralized meta registry that relies on GitHub authentication. And it also relies on DNS text verification for namespaces. So how does MCP work is essentially there's a publisher layer, and publishers use mcp.json file that defines the server metadata such as name, version, endpoint, capability, schemas, and all details about the server. Now they push this JSON file to a registry via CLI tool. So this authentication is on GitHub side. And then once it's verified, we are uploading the mcp.json file with versioning, and it is basically stored as a raw JSON file. Now, in its registry core layer, there is pretty much the acceptance of, let's say, there's read endpoints that anyone can call without authentication. All of that is done by Go-based REST API. There's write endpoints that requires GitHub OAuth DNS proof for certain namespaces. And then the Go-based REST API can also process raw JSON manifests that are stored in object storage, indexed in MongoDB for query. And if the MongoDB fails, there is an in-memory fallback to avoid downtime. There's also asynchronous job or webhooks that can trigger on the new publishers. Now, on the consumer layer, the MCP client libraries or the command line tool polls the central registry periodically. So they cache the mcp.json file locally and serve millions of end users without hammering the central service on every request. Now, if we compare this on the security side, you can see that the registry only accepts metadata from authenticated GitHub identities, and for domain scope namespaces. that could be DNS verified as well. So it does not host any executable code. Instead, it holds metadata only, inheriting that code level security from established registries. This kind of minimizes that attack surface and delegates authentication and domain to those proven systems. Kind of it follows from the previous point that authentication is done through GitHub auth bearer token, which is essentially tied to submitting user or organization. So only for the reverse DNS namespace, for example, com.microsoft, a DNS TXT record proof is required, and that is linked to that GitHub identity. So read operations are only openly accessible. Now, moving on to scalability for MCP registry, there's only a small number of MCP client application that can query the central registry. So they cache and serve data to millions of end users. The API supports asynchronous processing in webhook. Metadata is again stored in MongoDB, which is suitable. And it's basically served in the CDN cacheable HTTP endpoints. Optionally, there could be a middle layer for private mirrors, curated feed that can share load. Now, on the maintenance side, if we look at the registry is basically a schema-driven approach, which is having the mcp.json schema define exactly what fields are allowed, such as version, name, description, endpoint, URL, input schema, output schema, and there is no code hosting. So it only stores like raw JSON that technically limits the risk of malicious arbitrary code in the registry. And then there is a simple CLI that automates the publication process. If the schema needs to evolve, you need to update that JSON schema and then redeploy. It does not require rewriting the registry logic, but it requires you to upload that schema again. Again, because of this validation happening on the publisher side, the registry only needs to verify signature or authorization that is stored on JSON and index it. So just a quick recap of MCP towards the pro side. It's centralized, easy to query with simple REST API, has strong namespace control via GitHub DNS. Verification, it's able to offload caching to clients and CDN to kind of try to scale up to millions of lookup. On the con side, it's fully centralized service, so any single point of failure, unless there are multiple mirrors, that could be a problem. And then there's no built-in privacy paths to look up that would reveal which agent is querying, and it only fits MCP compatible agents. Now, as we move forward, now I'll go over to agent protocol. Now, an agent-to-agent protocol is essentially not a registry in the same sense as MCP was. Instead, it's more of a transport agnostic protocol for agent-to-agent communication. It uses a simple JSON manifest, which is called as agent card, to advertise the server agent's endpoint and capabilities. So A2A aims to unify how heterogeneous or cloud source agents discover and interact with each other. It's basically JSON RPC 2.0 over HTTPS, but with some conventions around task, capabilities, and streaming. Now, as I said, A2A has agent card, which is again a JSON file. It's typically served at the well-known URL with agent.json file on the server domain, or it is published in the central catalog. This agent card would list details like ID, name, description, version, skills, or capabilities. It will have information like security schema, and then would flag for any push notification. So this agent card does a one-step fetch approach, which uses that get and then your dot well-known agent JSON URL, and that returns basically the agent card. And from there, client knows which RPC methods are supported, which HTTPS headers to include for authorization, and whether streaming or webhooks are available or not. So that's just a little bit about A2A. On the security side of A2A, it typically relies on HTTPS plus TLS for transport security. So every RPC call is end-to-end encrypted. It identifies its identity is verified by the TLS certificate chain. The authentication tells us what the server expects, like whether it's expecting a bearer token, whether it's expecting an API key, and if the client does not provide the right token or header, the server can return 401 unauthorized. And for long running task, if a secondary credential is needed, such as like OAuth token for a third party API, the task state transitions to, let's say, authorized required, and then the server sends back a capability error indicating provide API key to continue. So this is kind of how the client can resubmit with the updated header. So this design reduces that attack surface, and agents would never share their internal state. Each RPC call is authenticated independently, and if the request fails, let's say in mid of task, it does not crash the entire workflow. On the authentication side, we've seen that agents card are explicitly support authentication mechanism like open API style security schemas, like I've mentioned, bearer token, open ID connect API key. So client must obtain credentials out of band and include them in the request header. Each of these RPC calls would include the same, like the appropriate headers. And then again, if the task would need more credential mid-execution, the server replies with that input required. And this will eliminate the bespoke authentication protocol inside the agent payload, reuse standard, HTTPS authentication best practices. Now, on the scalability side, A2A is task-based. It's stateless transport over HTTP and SSE, enable horizontal scalability across distributed agent system. So agent is able to, let's say, define its capabilities in agent cards, allowing registries and discovery services to dynamically catalog available services. The tasks are long-lived object with unique IDs, status update, and artifact streams, and streaming can happen via SSE, and push notification would reduce the polling overhead. The task lifecycle would support like fine-grained eventing such as submitting, working, input required, enabling responsive and resilient orchestration even in failure-prone environment. On the maintainability side, A2A is intentionally simple and extensible. It is built upon the HTTP and JSON RPC 2.0. So it minimizes like custom logic, avoid bespoke protocols with agent cards and structured data formats like text part, data part, file part. It ensures consistent interpretation of messages while allowing modality diversity. So the schema evolution is flexible and agents can define their capabilities per skill, override input output MIME types, and extend their agent card dynamically. So just for the summary of what, or a quick recap of what agent to agent is providing. It's basically a transport agnostic JSON RPC over HTTPS. The agent card declares all capabilities, input, outputs, and auth in one place. It's extensible with JSON schema, so there's no vendor lock-in. The cons is there is no global index. You either fetch a well-known URL or rely on the curated catalogs. One more thing which we look forward with Nanda Quilt would be that there is cryptographic signing. So in agent to agent with agent card, there is no built-in cryptographic signing of the agent card itself. It relies on HTTP trust. And that's where A2A is not addressing any federation across different trust domains. Each domain hosts their own cards. And that's basically about A2A. Now I would like to uh, uh, welcome Abul to kind of discuss over Microsoft Entra Agent, then Nanda Quilt Agent Facts, and then to kind of conclude with the comparative evaluation and also look at the phase-wise evolution of these registry types. Thank you so much for listening. Abul, whenever you're ready.
Are you able to see my screen?
Yep.
Yep. Thank you, Aditi, for very valuable insight, and Pradyumna and Jared and Ramesh for all this information on the different, especially on Nanda Quilt and how the agent facts and agent card works. With that, I will go and start with the Microsoft Intra agent, which is still in the public preview stage. And this one, it's like provides, it's fully controlled by Microsoft. It's managed enterprise grade directory it has, and it has the agent identities and agents created either in the Copilot or the Azure AI Foundry. It automatically appears as agent ID, which helps in it helps in understanding what are the different agents are present and how it interacts with the system. And with that, it's like how it works, how it goes behind the scene. Everything is controlled inside the Microsoft Intra Agent ID. Right now, if I zoom in, if you see that it is available only in the Foundry or Copilot Studio, the comings are the security Copilots and the Microsoft 360 and third-party registries as well. So if we see here, especially in the especially here is like it's used the upcoming feature include the least privilege token issuance and as well as the expanded conditional access and cross-tenant identity federation. This is fully controlled by Microsoft. It is in the public preview. We don't find much information about its security, authentication, scalability, and maintainability information. With that, I'll move to Nanda Quilt, how it works, what's behind Nanda Quilt, and how it's going. So with the Nanda Quilt information, Nanda Quilt provides a registry that addresses the needs of decentralized, privacy-sensitive, and federated environments. Think like think agent network, open research, and agent-to-agent collaboration across organization. At its core, if you see here, it has the at the lean registry level, it has the agent registry, which is compact signed object that links an agent identity to 3 key resources like fact URL, adaptive URL, and the privacy URL as well, which is private fact URL. These records are only about 120 bytes and cacheable and designed for high churn environment. Nanda architecture consists of 3 layers. A registry layers that maps the IDs to metadata pointer, an agent fact layer that containing W3 verifiable credentials, and a dynamic resolution layers. Let's talk about how it is different in terms of security, authentication, and the maintainability as compared to MCP A2A. So if we talk about security layer, each agent address is signed by issuing registry. The agent facts are verified using W3 verifiable credential, and it has the short-lived credential less than 5 minutes, and revocation via verifiable credential status lists ensure real-time control. The authentication part is decentralized. Agent uses identifier and claims like capabilities, certification, or audit result are issued by credential authorities bound to a specific trust domain. Scalability is like is also strong. Nanda offloads metadata to independent resource, reduces registry rights, and supports caching with TTL-based policy. The registry helps in short-lived credentials, and we talk about scalability. Scalability is inherently scalable due to its lean core and separation of concern. By reducing the registry entries to sign pointer and offloading the metadata to self-hosted or distributed stores, this is how it maintains the scalability and enhances the system. In terms of maintainability, it's like the core logic is deliberately minimal, stable, and reduces the operational complexity. Since dynamic agent state is handled externally via signed agent fact, registry updates are rare, and schema evaluation does not require code services changes. This decouple enables faster interaction on agent metadata without risking registry consistency. Also, it adheres to JSON LED-based schema with forward compatibility built into context definitions. When we see about the comparison of AI agent registry compared to A2A, MCP, and Nanda quilt, you can see it. They have different purpose. It's like how it depends upon and how it has a different discovery path. If you see the MCP talks with the server's endpoint, which is a RESTful API, as well as if you need a specific information about a particular server, you will go with the server IDs. Similarly, the discovery path for A2A is like well-known JSON format, and the two-step fact URL is for Nanda quilt, where we have a fact URL and private fact URL, which gives privacy as well. The trust mechanism for it's a bearer token, GitHub-based OAuth, and it has plain HTTPS and optional token, self-declarative attributes. It has W3 verifiable credential, V2 signature, and verifiable status revocation, support for third-party audit attributes as well. In the privacy option, if you see, A2 does not have that, but if you see, Nanda quilt has the private fact URLs and hide requested information as well. The endpoint refreshness, it has created at and updated at information, but I don't think so. We have, as per here, we don't have no TTL field here. But in the Nanda quilt, we have TTL scope list static for static, it is 1 for 6 hours. For rotating, it's 5 to 15 minutes. The best use case is like centralized registry of agent, especially for the tool context when you want to give to LLM. It is a stable for the A2A, on the other hand, is for a stable SaaS agent inside a single marketplace. Highly mobile, privacy sensitive, safety critical agent at trillion scale. If you need that, if you can see from here, if you need that, I think Nanda quilt is going in that direction to support the trillion of agents. Similarly, if we talk about how different is the agent card and agent fact, MCP does not provide much information about their MCP JSON information, but on the agent card level, if you see here, both have their identifier as ID. Nanda fact has an ID, but agent card depends upon the host URL. They provide label description. What differentiate, if you see in this table, it's like the routing. Does A2A has a routing? No. the Nanda agent fact gives the routing object and the adapter router as well. They both have the skill array, but the authentication schema is different for agent fact and the A2A cards. If we talk about protocol flags, they have the streaming information, but here also we have the streaming information, but the SBOM integrity, it's absent in the A2A, but we have in the Nanda quilt. Telemetry endpoint, we do have at Nanda quilt, it is absent here. Performance audit, you can go the evaluation block of object in the agent fact, and then the privacy fact URL definitely gives you much advanced method for privacy. The cryptography wrapper is plain JSON HTTPS, which is optional, and here we have JSON LAD W3 verifiable signature. The TTL time to live and freshness is not there in the A2A, but we have at Nanda quilt. And the revocation speed, it's a HTTP refetch, and it is less than a second with verifiable status. Let's talk about how this phase-wise is gonna going towards agent registry. We started with the static isolated discovery with the agent, well-known agent JSON file, as well as in the second phase, we started with the RESTful APIs through MCP, giving through the different endpoints to discover the agent or push the MCP JSON file via the CLI, as Aditi mentioned, how it works with the authentication and authorization, how we need to push those MCP JSON file to get the published information for the other agents to discover. Similarly, if you need something in the phase 3 with the verifiable metadata and federated trust and AI agent of quilt, I think we need a registry where we can have a W3 verifiable credential, PKI certificate, JSON hashtagging, and ID-based identities and domain bound signature to ensure authenticity. And also, if we need time to live caching and everything, then I think we are going towards the phase 3 of, I think this approach is closer to what Nanda is presenting in their paper. As per the conclusion, let's talk about how it's going. The registry architecture trade-off are protocol dependent. It's like if you see Intra is like more towards the enterprise ecosystem. MCP is great for dev-oriented, GitHub-based discovery, and also especially for the tools that required for the agents. It's more toward that. But for decentralized privacy environment, Nanda provides the most adaptable and secure framework. Let's talk about what we can conclude from the decentralized enable long-term sustainability. Which registry can give you that decentralized, which is equivalent to long-term sustainability? Nanda avoids centralized bottleneck by supporting federated trust, lightweight design, dual path resolution, ensuring resilience and scalability for the long-term goal. We talk about security must be built, not bolted on. So what's there in this part of the conclusion? It's like we need to think about security first. Only Nanda separates identity resolution from the dynamic metadata, allowing for tamper-proof agent verification, real-time revocation, and privacy-preserving interaction. We talk about interoperability remains the critical gap. So in terms of agent ecosystem, will needs to share identities and capabilities across platform. Nanda schemas, flexible, verifiable credential-based approach lays the groundwork for this. So if you talk about the next challenges that we are facing in the industry, I think Nanda is going towards to solve that issue. The community governance will define the future, like DNS and email agent infrastructure must evolve through open standard and multi-stakeholder governance. Proprietary models like Intra are valuable, but systems like Nanda are essential for internet AI agent to thrive globally. With that, I would like to conclude and say that we can think Nanda can be considered as superset in the sense that it includes core features like of MCP and A2A, like a static endpoint and basic metadata publishing, enhances them with the cryptographical security, privacy preserving resolution, and dynamic routing, and supports broader use case from centralized enterprise to decentralized agent of network. Thank you. I think Pradyumna, you can go ahead.
Thank you so much, Abul. And thank you so much, everyone. Great presentation. As I mentioned on the chat, we will conclude this Nanda paper session over here. We had three very detailed presentations on three of our papers. We do have a fourth paper as well, which is Nanda plus ANS, which due to lack of audience time and presenter time, we will move to next week. So please subscribe to our Nanda Luma page for all updates on future events, and have a look at all the papers linked via the GitHub link in the chat here. Thank you so much to everyone for joining. Hope you were able to take away uh, uh, the crux of what we are working at over here in Nanda. Of course, despite the detailed presentations, there are so many informational points that could not be covered in the presentation. So would encourage all of you to look up all the papers. And with that being said, thank you so much to everyone for attending, and see you at the next Nanda event.
Thank you.
Thank you, everyone.
Thank you.
Thank you.
Thanks, everyone. Bye.
Yeah, thank you, everyone. Bye.
Bye.